Thank you for joining us for our discussion on the advancements in Real3D surface analysis. This is Paul Thompson, and I will be presenting on this topic. Before we begin, I will cover a few housekeeping items. At the bottom of your screen are icons for our multiple application engagement tools you can use. All the engagement tools are resizable and movable, so feel free to hide them, resize, and reposition them to get the most out of your desktop space. You can expand your slide viewing area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A engagement tool panel. We will answer them during the webcast, and if a fuller answer is needed, we will answer it during the Q&A session at the end, or if we run out of time, they will be answered later via email. And know that we do log all the questions for us to follow up on. A copy of today's slide deck and additional help materials are available in the resource list. We encourage you to download any resources or links that you find useful. With that, let's get started. Hello, this is Paul Thompson, and I am with Clark Bendel today. I'm going to ask Clark to introduce himself to us. Clark?
Thanks, Paul. Yes, I'm Clark Bendel. I'm the RVI Technical Product Leader and a Principal Engineer with the business within Waygate Technologies. I've been with this group for coming up on 23 years now and spent a lot of time doing development work on our Real3D technologies as well as video and image processing.
Thanks, Clark. And as Clark said, he's been here for a number of years, and Clark and I have had the pleasure of working together for 22 years that I've been with the remote visual inspection business, starting with the Everest Imaging Group in 1998, through to Everest VIT and GE Inspection Technologies, now Waygate Technologies remote visual inspection business. And I've had the real pleasure of working with Clark on various unique technological advances that he's brought to the business, and it's only happened by having these kinds of discussions and listening to you tell us how you think we can do things better. So Clark's going to be monitoring the questions and answers during this call, so as I said, please use your Q&A tool panel on your desktop, and any questions we don't get to during the call, again, we'll answer them at the end or we'll get emails back to you. Clark, thank you. When one needs to understand the size of an indication, having both precision and accuracy when measuring are extremely important. And people do measure for a lot of different reasons. In aerospace, they're looking for safety of flight decisions, or in a lot of different scenarios, people want to know if an asset can be returned to service, or if the operations can be extended safely and then do some additional maintenance and outage planning. And when people think of sizing an indication to determine those things, they're doing it in multiple different asset types, whether it be in turbines where they're looking for the blade tip to shroud clearance, or whether a FOD impact foreign object damage has caused damage beyond limits. In some cases, parts like stators will start moving, and there's a stator rock inspection that is required. In piping and in various assets in a plant. Erosion and corrosion pitting are also of interest to know if too much material has been lost. And in critical welding situations, people are looking at reinforcement or re-entry angles, or looking for various weld issues. That is a short list of typical applications. I'm curious to find out what are the most common measurements you need to perform. So let's look at those things today. Why people measure, how they measure, what they measure, and are they getting good precision and accuracy. So In today's agenda, we're going to explain what Real3D measurement technology is and how it works, and we'll look at the solutions that it provides. We'll do some demonstrations on how to avoid common measurement errors that do happen. We'll look at some recently added measurement capabilities to this Mentor Visual IQ video probe system. We'll also be talking about some additional resources for you, and then we'll have a question and answer session. You'll be looking at images coming from either the Mentor Visual IQ video probe with the most current software level. This is the flame-colored handset, and the off-board or on PC remeasurement software is Inspection Manager, and we'll show you some images from there also. For today, what we want to accomplish is to provide you with an understanding of the mechanics and the technology behind Real3D measurement and how it works, and to help you identify and avoid some of the common pitfalls. And we hope to increase the confidence that you have when you're using a video probe, and that you can increase your accuracy and precision when obtaining measurements in the field. The two measurement technologies we're going to spend most of our time on today are 3D stereo, which is a measurement technology that utilizes the same optical tips as traditional stereo measurement, but it employs more advanced calibration and processing algorithms to generate a fully surfaced point cloud, which represents a target more accurately, and you can then view it, manipulate it, and analyze it, instead of only getting data where cursors are placed with standard stereo measuring. Then 3D phase measuring with structured light, or 3D PM, employs patented structured light patterns which are projected onto an object to create a fully surfaced 3D scan of the viewing area. And that allows you to measure all aspects of the surface by, again, pivoting this point cloud. What is a vast improvement and definite time saver is that with the same optical tip adapter that has a wide field of view and a large depth of field, you can use that same 3D phase lens to inspect, find indications, and then measure those indications without having to remove the scope, put on a new optical tip, and then putting the scope back in with stereo tips, and try to find that same indication all over again. We call it measurement on demand. Let's talk for a moment about Real3D measurement and what Real3D measurement does. It actually combines an interactive fully surfaced point cloud for you to visualize with advanced measurement algorithms, as well as an insightful 3D surface mask that's fully pivotable. And then you have dynamic advisory messages to enable more accurate and precise and repeatable measurement decisions. To use any technology to your advantage, it often helps to have a fundamental understanding of what is going on so you can use that to your advantage. In stereo measurement, which has been around for decades and has been in video probes since the early 2000s, there is an optical tip adapter. You'll see that round cylindrical item in the middle that has a patented splitting prism in the middle that splits the image into a left view, that's the aperture on the left, and a right view, that's the aperture on the right. And those two views are overlaid on top of each other into an overlapping arrangement so that this 3D coordinate matching system can look at a pixel in the video path on the left and that same pixel in a video path on the right, and use that to calculate XYZ data. So you'll see that spatial separation on the right-hand side. Objects that are close to the camera and have a small tip to target distance are going to be positioned more towards the center of the screen on the left and the right images, and objects that are further from the camera are going to be spaced further from the center of the screen, and it's that spatial separation that allows for calculating XYZ because the tip to target distance is known for each of those pixels. With this slide, I want to compare and contrast the differences between a traditional stereo image on the left and a Real3D stereo image on the right. On the left-hand image, you only have two white light images to look at. You have an image on the left from the left-hand side of the prism. You have that exact same image from that prism on the right-hand side of the optical tip. And you'll notice those cooling holes at the bottom are closer to the center. That blade is tilted away, so the top of that blade with these cooling holes, it's a turbine blade, and the top of that blade is further from the camera, so you see how they're spatially separated further out away from the center of the viewing areas. And so with that, you place a cursor on the left image, and the processor on the right-hand side has to find exactly the same pixel, or you will not get good data. And the same thing happens with the top image. Conversely, on the right-hand image with the white light image, on the left, you see the power turbine blade. This is a separate, different blade image, and they're measuring the gap or the distance between the tip of the blade and going up to the shrouded area. So the shroud of the turbine is actually masked in green, and that surface mask, I'll talk a little bit more later and the importance of that. But then you can see on the right-hand side in the point cloud, the image is completely pivotable in XYZ for you to determine, have you placed your cursors on the correct areas, and are you getting good results? Meaning, you could be getting very accurate measurements of exactly the wrong thing without a point cloud. And as I was saying, the power and the magic, if you will, behind this 3D visualization of a fully surfaced point cloud is that if you look on the left-hand side, you have two white light images, and you have to spend a lot of time understanding what's happening with that surface. In this case, it looks like a weld where the liftoff point was maybe slag or maybe some inclusion. It looks like that material is above the surface, but you wouldn't know that with 2D stereo unless you spent a lot of time looking at it. Whereas on the right-hand side, that point cloud gives you the ability to turn on a depth map. That's what you're seeing on the right, so you can see the variation in surface contours depicted in a colored depth map. And you can also pivot it, and that's what you're seeing on that pivoted weld just to the left of the depth map. So let's transition our discussion to 3D phase measuring with structured light. One of the very first things you'll notice if you look in the picture of that power turbine blade with the cooling holes is that it is a wide field of view. It's a 105-degree field of view from the corners of the images diagonally. And it's not a split image where you're using half of the imager on the left and half of the imager on the right. You go in and inspect and get measurements on demand with various optical tip adapters, whether they are forward view optical tip adapters or side view. And recently we've released a far focusing and farther measuring side view tip. That's the long one in the middle of the image there, and you can see the fringe patterns at the top and bottom, those fringe pattern generators that are above the optical imager. Now, you won't see this when you're capturing an image, but what happens is those fringe pattern generators fire sequentially and generate a series of shadows or fringe patterns onto the targets. And what is going to happen is that a series of these fringe patterns are collected and compiled to form an XYZ point cloud. As I mentioned a moment ago, you will not see the fringe patterns on the screen when you're going through the 3D capture of the structured light image. And I thought it would be interesting just to show you a sequence of what's actually happening. Clark actually captured these pictures, the one on the left. There are a series of white light images that are captured to monitor where the camera's position is to the target and look for any kind of motion so that those structured light images can be stacked up and create a very clean and usable point cloud. And then the white lights will turn off and a series of lights will fire in the fringe pattern generators. So as I said, you won't see this, but I'm going to show you a video where, again, Clark captured an image that will give you an idea of what it looked like. And keep in mind, this video clip actually cycles through twice, just so you can get a feel for what happens, because it happens rather quick. It happens in under 2 seconds. And that camera will sit still for 2 seconds, capture a whole series of white light and fringe pattern structured light images to give you measurement analysis ability. What you just saw in the video was two iterations of this sequence. So there are a series of white light images that are captured. In between the white light captures, on the left, there's a group of sinusoidally shifted image patterns that are captured where the LEDs fire and cause this phase shifting image to be captured. And once those are captured, they are wrapped together into a singular image. That data is analyzed and run through a series of algorithms. And with calibration data that is used on the optical lenses to the camera, they're put into an image that is unwrapped. And then from there, that data is used to compute X, Y, and Z for every single pixel that's holding enough data created from those fringe patterns. So when we launch 3D phase measuring with structured light, we have forward view and side view tips. And there are some scenarios when you're entering a casing or a turbine, or also in piping or other areas where you're inspecting, people wanted to have a larger volumetric area to measure. And as you can see on the left-hand side, the volumetric area for that blue tip is depicted. However, one of the things Clark and his team of optical engineers came together and built for us was the ability to do long-range measuring, and also a larger volumetric area is possible now with this far-focusing green side view 3D phase measuring tip on the right. Now, let's move on to a discussion about the various types of measurements that are available in Real3D. And there's 8 different ones. Some of them are very unique and only found in the Mentor Visual IQ video probe. As the creators of the world's first video borescope, we were also the first to bring measurement to industry on a video borescope. And a part of that development gave us the ability to measure the length of an object, or make a point-to-line measurement, or measure with depth measurement types where you can measure above or below a plane. You could use multi-cursor measurements to measure the area of an object, or also a multi-segment distance measurement. Today, those are also available now with Real3D measurement with a fully surfaced point cloud and the algorithms sitting behind those to give you the best chance for precision and accuracy, and also dynamic messages to let you know when you could possibly improve your results. What we've done uniquely just recently is also given you the ability to measure with a depth profile where 2 mathematical planes are established on a surface, and you can evaluate the contours or surface profiles and see the height above or below the plane. And that only gives you one measurement line, whereas with area depth profile, it can actually make a similar measurement, but over very large areas that are on 2 concentric planes. And then, if you want to be able to measure where the material was but is no longer there, measurement plane actually projects a plane into space and allows you to measure upon it, which is a facsimile of where the material would have been. Let's have a discussion on common measurement errors and how to correct or prevent them. Keep in mind that not all surface types nor all indication types may be measurable. I'm curious to know, what measurement types do you need to make and cannot make with your video borescope? So when measuring with 2D, and this would be with a stereo measurement type, these are some of the mistakes that are easily made and are very easily compensated for and corrected with a point cloud. People tend to measure from too far away and may or may not know it. They actually have made very gross errors in their misinterpretation of the surface's shapes. If they're measuring off angle and not understanding that, they can give actual data errors. The plane that they're measuring on is tilted to the actual surface's plane, and you wouldn't know that your measurement plane is separated without a point cloud. And it's very easy to miss the deepest point in corrosion, erosion, or other indications that separate from the normal material surface. Let me switch over now and show you some of these unique measurement types on a live demo. Now that I'm switching to a demo mode, I want to show you a few things that are going on. You're currently looking at my screen on my Mentor Visual IQ sitting here in front of me. I've taken the video output and I'm running that into my laptop computer. And you'll see my mouse moving on the screen. I actually have a USB wireless mouse plugged into the IQ because I find that moving cursors in a point cloud is much more precise and easy, quite frankly, than doing it with my finger, which has a much larger surface area than this mouse. So I also want to start with an example of where 2D mistakes are made when you're looking at a standard stereo 2D measurement. And that's when the reference plane that you're measuring from or to is actually tilted with reference to the surface. In this case, we're looking at a standard stereo measurement that I pulled up from the file manager. And in this case, they're measuring a power turbine blade, and they're measuring from the tip of that blade down to the shroud. So what's happened in this measurement, if I double click in this lower area, you'll see there's a toggle area that I can completely mask out and hide, and I can activate the measurement data. And what my task is as an inspector measuring with stereo is to look at cursor 1 on my side and the placement of cursor 1 on the computer side, and those have to be on exactly the same pixel, and if not, you will not get an accurate measurement. So I look in my zoom window for my cursor on the left, and I look at the processor's cursor in my zoom window on the right, and this zoom window is capable of moving the cursor 1/3 of a pixel at a time for very fine placement. So I look at visual references. Here's an artifact just to the left of the crosshair at the tail. The tail's on the blade. Here's that same artifact just to the left of the crosshair. The crosshair's tail is on the blade. And I look at the area around this, and I look at the image and look at where my reference plane lines are coming out of the cursor and do my best with as best precision and accuracy as I can verify this cursor and this cursor are exactly on the same pixel. And folks, if it's not, you just simply will not get accurate measurements. So that's problem one. It takes a long time with a stereo measurement. So I can then click on the second cursor, click my mouse. This cursor is now active, and I'll look at the two artifacts just below the crosshair, similar to artifacts just below the crosshair, darker area out at the tip at 90 degrees. And then I can also press the enter key on the IQ, enter, and it will cycle through and again look at the artifacts, look at my placement of my cursor, look at the computer's placement of the cursor. And once I feel comfortable that my plane is established correctly on the shroud, I can then measure here at the tip of the blade. And when I look at this, I'm getting 43 thousandths from this point to this shroud, or to the mathematical plane that is on that shroud. Looks like I'm not quite on it, so I will click at 12 o'clock on this caret. 1, 2, 3, and in fact it changed at 1/1000th of an inch, and not a remarkable amount. One goes and looks at the manual, determines if they're close to passing or failing, or if it's completely within reason, and starts making judgments. And you never want to make a call based on one picture. So that's how you do stereo. And with 3D stereo, you have some tools that are available to you that aren't available in traditional stereo. Let me turn those on for you. If I go to the menu, down here is a hot area. I can touch the global menu, go to my settings. in my measurement annotation, I can turn on the surface mask, something you hadn't seen before, and I'll show it so we can now have some data to help me and understand what's going on the surface. This data that's green, data that's masked in green, are points on the surface that are very close to this mathematical plane. So you see I have no data points along two of these lines, two of the legs of the plane that have no masked green data. And then this blue surface mask is data that is 42 thousandths of an inch perpendicular to that measurement plane. So you see I have disparity here, and it shows up over there. There's definitely something going on here, and you just simply would not know that without a lot of work at understanding what's going on with a 2D image. But with Real3D, in your views mode, you can actually go into a split point cloud where you're looking at the white light image on the right, on the left. On the right hand side you have your point cloud, and you can see the points. There's your triangular plane, and as I click on the bottom where this blue reference plane is bounding the area, and it's an extension of this mathematical plane out into space, if I click it on the bottom and start lifting it up slowly, what I can do when I get a single blue line, I'm looking straight across that mathematical plane. So you see the 3 points here. So there they are. And here's one up on the blade. Let's rotate it 90 degrees to the right. And all of a sudden, you now start to realize that this point, which is this point, and if you noticed, I clicked on that point in the point cloud. I can now move these points in Real3D point cloud, and you notice that your reference plane is tilted to the shroud material, and it just completely is not the measurement you want. Is it really 42 thousandths? No. Let's go to a full point cloud view and make this cursor active. I clicked on it with my mouse. I'm going to bring it down to that shroud, and instead of 42 thousandths, I'm getting 62 thousandths. So again, all of this blue data mask is data that's 62 thousandths of an inch from this mathematical plane, and 62 thousandths is significantly different, we can all agree, from 42 thousandths. So that's one example. I'm putting two fingers on the map just to show you the versatility. On the depth map, on the point cloud, I'm putting two fingers on it. I'm putting one in this area, one in this area on the point cloud, and rotating it to get the best view that I can, zooming out to see if the surface data, this surface data is nice and smooth, just as I saw in the white light image. And so you can now see that all of this data that's masked in green is actually on the shroud. Where I had the cursor before was up here. This red data is unmeasurable data. You want to avoid measuring around red data or unmeasurable data if at all costs, just because that data is not necessarily stable or viable right around the fringe areas. So I'm now moving this down just to show you what we had. This is what we had. And there was a call of 42 thousandths. This is what we want. And that is how you can use Real3D point cloud to avoid that common error. In this next example, I am viewing a weld with a 3D phase measurement image, and I'm using my PC-based Inspection Manager remeasurement software. I will show you what can happen when you're measuring from too far away and the pitfalls of doing so, as well as how easy it can be to misinterpret the surface shapes. In this case, I'm evaluating a weld. The weld has a strike point or liftoff on the reinforcement. We'll want to evaluate that. It also looks like there may be porosity or shrinkage in the weld in this area just to the left of the strike point. We'll assess that using a depth measurement. I will place 3 cursors around the indication to form a flat mathematical plane by adding a depth measurement. You see, when I do that, the first cursor is placed, and when I press the enter key, I have a second blue cursor that is active, which I can use to form a plane around this indication. I can press the enter key again, drag that third cursor to place this flat 3-pointed plane, which is a flat mathematical plane between these 3 triangles. And then when I press the enter key again, Auto Depth Assist helps me find the highest or deepest point around that plane. You see it came up with a point of 0.000 of an inch right in the same area. So if I actually move this depth cursor on top of that indication, you'll see that I'm getting an orange bounded indication value as well as a dynamic message. And that dynamic message is telling me to move closer to target because I'm measuring from 455 thousandths of an inch away. And it says, or move the cursors for better results. I have the cursors where I want them. My only option at this point is to get closer to this indication than 455 thousandths of an inch to see if there's any depth. I'm not saying there is or is not. I'm saying I'm measuring from too far away to get a valid measurement. So, next, I want to evaluate the strike point. I will add a measurement type of depth profile where I can place one cursor, which you'll notice has no crosshairs in it, because this data within this area is going to form a mathematical plane where a point from the center of that data Next, I'll evaluate the strike point or liftoff point by using a depth profile. You see the symbol for a depth profile allows me to place one cursor on one side of the indication. Notice that it does not have a crosshair, and that's because the data in this area is being used to create a mathematical plane, and from that plane to the second cursor, it's going to look between those points and pick the highest point, which it chose here is 5 thousandths of an inch, 15 thousandths of an inch, which it chose at this point as 15 thousandths of an inch. Next, I will evaluate this strike point by adding a depth profile where I can place 2 cursors, and between those 2 points on a plane, it will pick the highest or lowest point. So you'll notice it does not have a crosshair because it's using this data to establish a point on this plane. I can place the second cursor across on the other side of the strike point, and you notice that it's picking this area is 12 thousandths of an inch. You'll also notice that these 2 cursors are not. You'll also notice that these 2 cursors are filled with red, indicating that there is something going on with this planar data where it may not be congruent with each other. You will also notice that the algorithm has checked these 2 surfaces, and it is determining that these 2 planes may not be congruent with each other, as if they're on a step above or below one or the other, or they may not be on angular alignments with each other. let's look at that data in a point cloud. So if I go to the full point cloud, you'll see the 2 points that were established by those two planes. The point that was picked here as 12 thousandths of an inch below the plane. And again, I'm measuring from fairly far away for a depth measurement. It would be good if I was closer. But the plane established by these two cursors extends out into space, and you'll see the reference plane. If I click and drag on the bottom and start lifting that point cloud, what you notice is that I'm actually measuring on an orbital weld on the inside diameter of the pipe's radius. So I'm getting inaccurate information. I'm not finding this strike point as the highest point. So the next step would be to go back to your normal image and measure on either side from pipe floor on the bottom to the pipe floor on the top. And you'll see that I'm now striking below or on the left side of the weld. And you'll also notice as I look at the point cloud that I'm not following the longitudinal axis. You'll also notice that you can see our measurement values on Real3D, or at least the cursors that are making up that value are visible through the point cloud. And it gives me a visual clue that this cursor could be walked up and you see it moving on the point cloud. Or in fact, I can also move in the point cloud by making this cursor active and coming across, clicking on this cursor and coming across. And you see this is taking me a very long time to evaluate that entire orbital strike point, the orbital weld's strike point. So you will see that it's taking me a very long time to walk across and evaluate that orbital weld strike point there, and I'm getting some 37 thousandths of an inch. But not all things are as they may seem. I'm getting 37 thousandths of an inch, and because I can add up to 5 measurement types, I'm going to place a depth measurement on this top pipe, and I'm placing again 3 cursors to establish a mathematical plane and measuring to the other side. And you'll see this green surface mask. That mask data gives a lot of reference. And what it's telling me is all of these points, except for this area here, are on the same general plane as my depth reference. But when I rotate that point cloud, you'll notice that I have a high-low at this point of some 15 thousandths of an inch. So I then have to reevaluate. This is not 37 thousandths of an inch because these two pipe floors are not congruent with each other. And this blue surface mask is showing displacement from my measurement plane. And I'll roll in with my mouse and you'll see that that blue mask here is representing the offset from my high-low of 15 thousandths of an inch. So not all things are truly what they appear to be. Then lastly, what I'll show you is a faster way to measure this entire weld instead of using a single depth profile. Let me delete both of those measurement types. Let me place a area depth profile where if I place cursor 1, and notice this one does have a crosshair. This is establishing one end of a plane, and this is establishing the other, and that plane is actually following the profile of this radius. And when I drop the third cursor on this side, then I can evaluate it. I notice that I'm catching some of the toe, so I can move this down to where I'm not catching the toe, and you'll notice that from this plane above the weld to this plane above the weld, which now are both following the pipe floor, it's taking hundreds of slices between these and capturing that as the highest point. And that's how you can look at some of the pitfalls, and that's how you can use these tools to avoid making these kinds of errors. In this last example of common 2D image measurement mistakes, I'd like to show you an example of what can happen when you're measuring at an angle and you don't know it. You can actually get very accurate measurement results, but they can also be very wrong at the same time. In this example, I'm using, again, Inspection Manager on my laptop. I'm looking at the inside of a compression section on a large frame turbine using a forward view phase measurement on demand tip. This measurement on demand is the one that generates structured light. That's why you have the full view. And the instructions or guidance were to measure from the near side stator and understand how far these stators may have rocked with respect to each other. And that's when you will see this indication of separation where these two stator floors are not congruent with each other. When this first came out, stereo was the only method that was available. You didn't have measurement on demand, and the guidance was to use a length measurement. So the inspector would place a cursor on the near side floor, go perpendicularly up the face, and put another cursor and look at these reference points, look at all the data, and make your judgment. I think it's 93 thousandths. With Real3D's point cloud, the idea now is never make a measurement call until you've looked at the measurement data. And what you'll notice is this cursor here on the near side stator floor is establishing a line to the next point that is not congruent to or perpendicular to the face of that stator. It's measuring off at an angle. And furthermore, I'm not measuring vertically up the face of that stator. Significantly in front of it on the near side stator floor, significantly around the shoulder on the far side stator floor, and because there is no noise, the XYZ data around this cursor and the XYZ data around this cursor are very clean and congruent with what I saw in the white light image. I would tell you that image, that measurement is giving me a fairly accurate and a very wrong measurement. So I'll reset the point cloud. In this case, I will go to the full image again, and I will add a measurement type where I can measure vertically and perpendicularly to this plane. So if I put 3 cursors in a depth measurement type on a surface, and those 3 cursors are congruent with that plane, you'll see a mask, a green surface mask, and that indicates all of the pixels that are currently masked in green are pixels that are very close to this mathematical plane of this depth measurement. I'll place my 4th cursor where I can measure above that plane, or if there were depth, I can measure below the plane. But I'll place it right here where the last measurement was placed, and maybe go up so it's completely centered on the same point. One measurement, I'm getting 65 thousandths. One measurement, I'm getting 93 thousandths. Can be worth several hundreds of thousands of dollars of production when the wrong measurement is called. However, I haven't called anything yet. I'm simply telling you I have a 65 thousandths of an inch measurement with this data, and I will look at the point cloud in the full point cloud view. The first thing I will do is look at the data that's on the near side stator floor. I want to make sure that all of these 3 points are on that flat part of the stator floor. They have not started separating from that surface, and you can see when it does, I'm separated from the stator floor, and in fact, intentionally to show the point, move this cursor up the leading edge of the stator, and I'm moving it back onto the near side stator floor. So when I look at that data, completely smooth, completely flat, this one may need to come down onto the stator floor, and I'm using my reference plane as a guide to tell me if in fact, and you can see what happens when I'm not congruent with that stator floor.
So after analysis, I feel comfortable that these 3 points are on that stator floor. So that's a good measurement plane to measure from the near side stator floor. On this point here, if I look at that point, rotate it in 3D space, I can tell that there is no noise around that pixel where that cursor is placed. And so what I'm telling you is this call of 66 thousandths of an inch versus the 93 thousandths of an inch is significantly more accurate. And after taking 2 or 3 more measurements of that, I would make a call somewhere in the area of 65, 66, 67 thousandths after I've done a 3-shot evaluation of this. And that's how to use Real3D point cloud analysis to avoid pitfalls, to get good indication measurement results, and how to increase your confidence in Real3D.
With what you've seen so far, I trust that we can agree on the fact that you can improve your RVI measurements with the use of 3D point clouds, and that measurement accuracy is essential and critical in RVI applications, and especially where asset uptime and safety of life are critical. As well, 3D phase and 3D stereo bring point cloud analysis to your toolbox on multiple probe diameters and give you a good chance of meeting your application needs in a variety of situations. So with this interactive 3D point cloud visualization, it will help you and your inspectors to avoid common measurement pitfalls. And hopefully you also notice that the point cloud rendering on the Mentor Visual IQ is smooth. It doesn't jump as you're manipulating it. You can position your cursors in the point cloud for a better measurement outcome. With that, we'll switch over and check what questions have come in and have an open discussion. As a reminder, there are resources available to you in the tools panel. You can do a free download of a measurement handbook that Clark, product manager Tom Ward, myself, and others have created to help you with the measurement process. And you can learn more about our video borescope. There are some links and literature to download. There's also a Waygate Inspection Academy, and we deliver classroom and online trainings. If you actually go onto that Inspection Academy, you will see that there are several courses that are no charge. One of them, I don't care what video scope you own, you should watch a 22-minute video probe care and use to reduce your cost of ownership and get maximum life out of that instrument. And then feel free to get with myself or any of your local sales professionals, and we can get you set up with an on-site application analysis with one of our subject matter experts. Now to the questions. And on behalf of Clark Bendel, myself, Paul Thompson, and all of my colleagues here at Waygate Technologies Remote Visual Inspection, we thank you for joining this webinar.
Good morning, good afternoon, everyone. Thank you so much for joining our webinar this morning. We are now going to be entering our live Q&A session that we have with Paul Thompson and Clark Bendel of Waygate Technologies. The first question, Clark and Paul, is where in the image does the MTD value refer to?
That's a great question, and I appreciate it. MTD is, I think you would have seen up on the top of the videos where, or in the images where it was displayed up on the top left, and MTD is a value called maximum target distance. So when you place a cursor on the screen, and the very first cursor on the screen, you'll have an MTD value assigned to that. It's helpful sometimes, especially if you're doing a tip to shroud clearance measurement, where you can put that first cursor on the blade and you'll understand the target distance for that one cursor, which is the maximum target distance. That actually will allow you to understand when you move that cursor from the blade onto the shroud, if you're on an area of the shroud congruent with the blade tip or in front of or behind it. So then when you place subsequent cursors, say You can place up to 24 cursors in an area or multi-segment measurement. One of those cursors, or all of them, could have the same MTD value. It's that distance from the camera to the furthest cursor on the measurement image. Great question, thanks. What other ones do we have, Meredith?
Yeah, next one is, are the depth measurements in a Cartesian or cylindrical coordinate system? And if you could talk a little bit about that.
Clark, I'm going to ask you if you'll talk to that one, please.
Sure. Yeah, so all the measurements are performed in a Cartesian coordinate system, and I believe this question was posted while we were talking about the weld measurement on a pipe surface. And so it is important when you're measuring on a surface like a pipe that is round, has a round reference surface, that you are careful to properly set up your reference plane for depth type measurements in that kind of scenario. So that's where the 3D surface mask and, of course, the point cloud come in handy, and also area depth profile can be a great tool in pipe type applications because it will follow the surface in terms of all the different slices that it analyzes. Each slice has its own individual reference plane that's set up to be tangent to the pipe surface at the location of the slice. So that's a really good tool to use if you're making measurements in pipes.
Mm-hmm. Great, thanks, Clark. What else came in,
Thank
Meredith?
You. The next one is, how is the measurement accuracy confirmed? Meaning, is there anything that it's calibrated specifically against any standard for each of the 3D measurements?
Right. Excellent question. And so that you're aware, when we manufacture these instruments, and they are manufactured at our facility in Central New York, the instruments and the measurement optical tip adapters leave the factory with a calibration certificate of calibration, and it is to a National Institute of Standards and Technology, an IST traceable kind of a process at the factory. And then the measurement tips are also shipped with a verification block that has very specific indications in them of 0.100 plus or minus 0.2 and 1 millimeter plus or minus 0.005 millimeters, and those are also traceable to NIST. So the first thing I would tell you is, I don't care what type of modality you're doing in non-destructive testing, you always want to validate that your instrument is in calibration, and that's how you do it on a Mentor. So the rest of the process then, after you are making measurements in a device or in an asset, is to do a gauge R&R. There is no video probe in the world that will make any measurement that you want it to make. There are just limitations with different technologies. That's why we at Waygate Waygate Technologies have UT eddy current. We have radiography, CRDR. You use those other instruments to validate your results or give your results when you can't get them. But with a viable surface target, and one where you can get valid XYZ measurement data on the surface, please don't ever make a call based on one image. Get 2 or 3 or 4 and do a gauge R&R on that given indication and on that given surface. Then, when you're finished, make sure that that same instrument can go back into that verification block and it's still operating within calibration standards. What else, Meredith?
Wonderful. And, during the presentation, we had some conversation sort of back and forth with some of the participants around getting an accurate measurement around weld inspection on round surfaces. So did you want to talk a bit about some of those best practices and capabilities?
Well, sure. So, yeah, understanding the surface profile is paramount. And so if you're using a traditional standard stereo that doesn't give you real 3D where you can look at the point cloud, it becomes difficult, somewhere around impossible. You can even, like I said earlier, get very accurate measurements, and they can be very wrong just because you can't tell what's going on as easily in two white light images like you see on stereo. So the idea on any surface that you're evaluating is to understand it. And the best way to understand it is to look at the point cloud. On the IQ, you can go straight into the full point cloud and look at that surface before you even begin to measure it, and look at the point cloud's health to see if the XYZ data very closely, if not specifically, replicates what the surface indication looks like. And then on some rounded surfaces, this is where area depth profile could be a very helpful measurement type to measure on curved surfaces. And I think you saw that when I was measuring that orbital weld, and I could not get a meaningful and quick measurement just using depth profile on one slice between two planes, and instead switched over to area depth profile, where I was sweeping across almost the entire visible weld profile and able to get that liftoff point's high point, at some 41 thousandths of an inch pretty consistently and often. And by the way, I was doing that with a full screen view, the 105-degree field of view. That's the other thing. You're able to understand surfaces better with phase measurement. That structured light tip is 105 degrees. It's not a split image. And so that's a significant difference that we have looking at any surface that just isn't available anywhere else. So what else came to play there, Meredith?
Great. So in regards to surfaces, does surface sheen affect phase measurement? And if so, how?
Another really good question. And let me just mention, we're coming up to the top of the hour. I see we have just under 3 minutes left. Clark, Meredith, and I have agreed to go over because there are so many really good questions. I don't know that we'll get to them all, but we are going to go 15 minutes over the hour and answer as many of these questions as we can. And then we have logged these questions during the call, and we'll get to all of them that we don't get to live in follow-up. So surface sheen, that's an interesting question. And observation, you'll see that in some turbines where you have highly reflective turbine blades, or you may see that in when gearboxes where you have an oil sheen. Sheen can mean a number of different things to different people. So because this is an optical metrology system, whether it be stereo or 3D phase, you have to take into consideration, what am I seeing on the surface? So with 3D stereo, because of the algorithms that Clark and his team have written, there's a much better matching algorithm, but sheen can still be an issue. And Clark's going to talk about a couple of tools you can use in stereo measurements to improve that process. And on 3D phase, you have to keep in mind there's actually two images that are going on. There's a white light image, I think you saw it in that video, where there's a series of white light images that are captured to look at the surface and determine if the camera has been stable, that we're still looking at all of the fringe patterns laying on the surface at the same spacing. So there's the white light image, and there's reflection in that. And separately, there's some couple of 3 or 4 dozen possible images that could be taken with the structured light, and the camera's also looking at them. And so when it takes all of these 30, 40 or so images and lays them on top of each other and stitches them together in a point cloud, that's your fringe pattern or point cloud image. And those two aren't always going to show sheen or reflection or the effects of those equally. You can have a lot of reflection or glare in a white light image and the point cloud look completely solid. So I would say get your best possible shot, think about both of those criteria, and then if you can't get a good shot, position the camera differently. So Clark, what would you have to say about that around stereo or anything else that I've shared there?
Sure. First, I guess on the question of 3D phase, a couple things you can do to maybe improve the performance on surfaces that might be on the shinier side. One would be just managing the viewing perspective with the 3D phase tip. So on shinier surfaces, if you view from a non-perpendicular perspective, so if you're, say, 45 degrees or so away from being perpendicular, that can often produce much cleaner 3D data than a perpendicular perspective. Also, the new green 3D phase tip, the longer range tip that was mentioned somewhere in the middle of the presentation, that tip can perform better for a lot of shiny surfaces than our standard tips, just because it has brighter projected patterns and a brighter optical system, and the projection geometries for those patterns is improved on that tip relative to the standard tips. So that would be worth looking at. On the 3D stereo side, we have a live image processing feature available in the image menu that we call Dark Boost. And when you're trying to capture a 3D stereo image for measurement, you're trying to sort of maximize the portion of the surface where you're trying to measure that is within the sort of normal brightness range, so not blown out white and not too dark. And so the dark boost control can really be helpful on these shiny surfaces by bringing up the brightness in those darker areas without blowing out the highlights. And so that can improve the results you get with 3D stereo on those surfaces as well.
Thank you. Our next question is, what is the precision on the tool, meaning how small of a defect depth can it detect and report?
Yeah, so I would say, in a broad sweep, that generally indications that are smaller than 3,000ths, 4,000ths can be lost in the circuit's noise value, if you will. So it's not really a good tool if you're looking for things that small. And then in general, there's a 1-to-1 ratio if you have a depth that has some value of, say, 0.1 inches across the top. In general, you can see the 0.1 inches in the bottom. However, it will not. It's an optical tool. It can't see around corners. So you have those limitations. You have to be able to see what you want to measure with 3D phase and get enough fringe patterns on that area of interest. And with stereo, you have to have a completely crystal clear image. You want to get as close as you can, as sharp a focus as you can, so that the areas of interest are in focus. But they both have similar limitations. And Clark, I don't know if you want to add anything to that.
Yeah, what you stated, Paul, is correct. And something just to be aware of with any of these triangulation-based optical measuring systems, the distance from the viewing camera to the surface is a very important part of the precision or accuracy. So the closer you get to the indication that you're trying to measure, the more likely you are to be able to resolve a small feature like that and get an accurate measurement. So you really want to get as close as possible while being in reasonable. Certainly with stereo, you have to still be in focus. With 3D phase, you can be a bit out of focus as you get in very close and still be able to resolve things like dents and pits. And the triangulation geometry improves as you get in closer. So if you're going after very small depth, being in very close to the point where things are a little bit out of focus is actually not a bad place to be with 3D phase. And we also have an even closer than standard focus forward viewing 3D phase tip, which is an orange color code. So if you do frequently make very small depth measurements, that might be a good tip to consider.
Yeah. Hey, Clark, I'll just mention quickly with that orange phase tip, I was asked if we could measure things that are around 20,000ths of an inch deep pitting on the suction side of compressor blades in a turbine. And So I used that orange tip, and I was getting 23 thousandths, 23 thousandths, 23 thousandths of the depth separating from the surface, and I told the customer that. He disagreed and did a replicast of it and put it on this very sophisticated machine that was also a 3D coordinate system that generated a point cloud. He got 0.023425, and so he said, oh my goodness, I sure thought it was much deeper than that. So somebody asked about precision and accuracy. With good technique that Clark just described, you can get repeatable measurements to the thousandths of an inch on length type measurements and depth measurements. You just have to look at the point cloud and look at what the underlying health of the data is. Health, I mean, are all of the pixel points and the Z value congruent with the surface that you're using for your reference plane. So great questions. What else is out there, Meredith?
Great. What is the spatial resolution that is achieved?
Well, again, it depends on the surface that's being evaluated. It depends on the skill of the technician. There was a question earlier, do we offer training? This is a non-destructive testing method. Remote visual, if you're more than 24 inches away from a surface, you're doing a remote visual test. And one that's doing those kinds of NDT processes need to have on-the-job training. The classes that I offer and other people around the globe offer, and the classes that are on our Inspection Academy, Waygate InspectionAcademy.com site. They give you a large foundation, and you have to then go put that into practice on site. And so the short answer is you have to do a gauge R&R with a person on a surface to determine what is possible with that given surface type. So it would be hard to answer a specific question around that without knowing the surface type, the indication type, and what level of experience the operator has. But those are the things: training, proper technique, proper measurement types, gauge R&R, and make sure the system is in calibration before and after you make your measurements. Yeah, thanks for that question. It's a great one. What else, Meredith?
So with missing materials, how are you able to measure missing material area, like in a compressor blade tip corner with 3D PM tips, and any best practices you can share on that?
Yeah, something that we've done that is significantly different is Clark and his team have created a tool called Measurement Plane. So old school would be, and old school is still available, you can do a point-to-line measurement. So if we're doing missing material, people are often talking about leading edge or trailing edge tip of a blade that's curled or completely broken off from foreign object damage, right? So in those cases, what people have done for years is place a point-to-line measurement where the line is established with two cursors on the tip of the blade. And then from that line, you measure up the leading edge or trailing edge to where the material is. Old school, difficult with traditional stereo that we still offer on some of our instruments. And it can be very accurate. You have to practice and get used to understanding what's going on. But with a point cloud, it becomes obvious with that point-to-line measurement if and when you're making good or bad judgments. And then you have to do two of them, one on the tip up to the leading edge, and then one on the leading edge down to the tip. It's much faster. I mentioned Measurement Plane. Measurement Plane is an app that you can install on a measuring system, meaning we have three levels. There is an inspect platform. We have an app for that called Measurement Plane. On the touch platform, there's an app for that. It's also Measurement Plane. And then for those of you that have SYS3 type systems, it may or may not have it in there depending on its vintage, but all of the current SYS3 or analyzed video platforms that we have in the Mentor all have this Measurement Plane in there. Sounds like a long question, but it's a fun kind of thing to play with. You put a measurement plane on the surface, meaning you put three cursors on a plane. It establishes the mathematical plane on that surface of the blade and projects it into 3D space in all directions, including where the material is placed no longer. And then you use an area measurement. So those two things together, measurement plane and area measurement, are used to then, on that area measurement, place up to 24 cursors around that area that's missing, and you're placing it actually on the plane of that measurement plane. And then look at it in the point cloud and understand, have you placed your cursor correctly, meaning the point out there in space that's on the tip or where the tip would have been, and you can see the reference lines lining up with leading edge, trailing edge. Some of those things are much easier to see when done live. Go off to our inspection manager and download it on inspectionworks.com/support. And if you have Mentor Visual IQ, start playing with those kinds of measurements. What other questions are out there, Meredith? We have about 4 more minutes remaining.
Yes, no problem. I understand. And any open questions that we have from the attendees and from the audience, we will definitely be following up with you directly to provide additional details. But for the last question, does the orientation of structured light lines relative to the measurement axis affect measurement accuracy?
I'm not sure who asked that question, and it is a very astute question, and the answer is yes, it very much can be. In other words, structured lights on 2 of our tips are projected in a horizontal pattern, and on 1 of our tips it's projected in a vertical pattern. And you want to maximize the amount of these fringe pattern projections that you have on any surface to give you your best chance of getting good measurement data. So that's a short answer. And Clark, I don't know if you want to expand on that at all.
Yeah, so I guess where I would say that may come into play the most for some of our customers is looking at things like turbine blades, where the blade might be coming right toward the camera and you just see a very narrow portion of the blade in the image. And in those cases, sometimes you may have a little difficulty with the standard blue side view tip because of that pattern orientation. And the new green long range tip has the horizontal line patterns and can sometimes work better in those situations. So if you are doing compressor blade measurements or turbine blade measurements, and you often have that viewing perspective with just a narrow blade in the image, I would certainly suggest giving the new green tip a try if you're having trouble with the standard tip.
Great, thanks, Clark. Meredith, back to you.
Right. Thank you, Clark, and thank you, Paul, for your time. I wanted to thank all of the attendees for joining us sort of all over the world. We really appreciate the time you spent with us, and we will be following up with any open questions directly with you. We will be also providing as a follow-up this recording for your reference in the future. Thank you again so much for your time and joining us at Waygate Technologies for our advancement in Real 3D surface analysis. Have a wonderful day.